Hello students, welcome to my class on operating system. I am Shravani Kundu, Assistant Professor, Department of Computer Science and Engineering, Guru Nanak Institute of Technology. Today I will discuss process state diagram and context switching. So this is the overall objective of this lecture, and after going through this lecture you will be able to create the process and you will be able to explain the different states of the process. So the first thing which I will discuss, what is process? So as you see over here, the process is a program in execution. So this is the smallest definition of the process, but it carries lots of meaning. Now what do you think, what do you mean by a process is a program in execution? So here two important terms are there. The first one is a program and the second one is a execution. So two important terms are there present. First one is the program and the second one is execution. Fine. So let us define what is program. So as you know that program is nothing but a set of instruction. So suppose if you write a code like this one, if you write a code like this one, main, I am writing a simple C code. Here I am calling a function if, and inside this function if, I am performing some addition, C equals to A plus B, and before that I am taking the input for A and B, and then I am showing the output. That means I am displaying the result of C. Okay, so this is the smallest program, a very small code. So we can say that this is a program because it has a set of instruction and it will fulfill some action. That is, it will take the input of two numbers and add them and produce the result. Now, while you will write this code in any editor, and after writing the code, when you will save it, then it will be stored in your secondary memory. So as far you just save the program, it is save the code which you have written in the memory, then your code is nothing but the program. It is not the process. Okay, so program is not the process. You have to remember that thing. This is very important decision, consideration, that program is not the process. So program is a set of instruction which we will write and we will save it in the memory. So suppose we will save the program with the name file1.c. So file1.c is the name of the program. Now, while you will execute, you want to execute your program, so you will definitely write this execution code. If you use the GCC compiler, you will write GCC space program name .c. You will press enter, and after successful compilation, you will run your code by writing ./a.out. So by writing ./a.out, you can execute your code. So while you will execute your code, before execution, your program is now converted to process. So without conversion of the process, that means program is not able to execute by itself. Okay, so program has to be converted to the process and then the process can execute it. Okay, now, so what happened after that? So while we want to execute this program, then it is a process, but process is not only has the program, other than the program, it has some other resources. So if I analyze this code, you can see that to execute this program, I need to call the function. And as you know, to handle the function, what I need? if I want to handle any function in my program, I need stack to handle the function. Okay. Now, inside the function, we are taking the input for A and B. That means I am calling the input device. I should write it is only the input device. So while I am taking the input in the variable A and B, I am calling the input device. That means I need to invoke the IO subroutine, IO services of the operating system. So what in turns taking the help of the input devices means I need to call the IO services of operating system. Fine. Now after that, after taking the input A and B, what we have to do? We have to perform the addition and we will store it in C. Now to perform the addition, we need the help of ALU, arithmetic logic unit. We need the set of register to store the intermediate data. Fine. Now after that, after performing the addition, we are displaying the output through the output device. That means through the monitor. So what I need? I need the access of output device. Okay, I need to access the output device. Again, to access the output device, I need to call the IO services of operating system. So you can see that to execute this simple program, I need a lots of resources. I need stack, I need input devices, I need ALU and register to perform the execution, mathematical operation. I need the help of the IO services to display the output, and apart from that, I need the space in the main memory. So I need space in main memory to store my program, because while you will execute your program, the program must reside inside the main memory. If the program is the CPU cannot execute the data by fetching from the secondary memory, CPU always can access the main memory. Fine. So definitely I need to store the data in the main memory. That means while you have a program, that program is nothing but a set of instruction. But while you are talking about the process has the program, and apart from the program, it has another set of resources like some memory. It needs to handle the IO resources. It needs to handle the CPU clock. It needs to access the ALU. It needs to access the register. It needs to access the file, and so many things. As per the, depending on the instruction present in the program, the different types of resources the program needs to complete its execution. Fine. So what we can say that a process is not only a program, it is a program. So what we can say, we can write down like this one: a process is equals to a program and some and the other resources of computer. So these resources can be anything, whatever the resources. It can be the tangible resources, it can be the intangible resources. Tangible resources means that IO devices, the ALU, memory, those are the tangible resources. Intangible resources means I need to call the different subroutine, I need to call the system call, I need to access the different files, different programs. So I need to access all of them. So those are the intangible resources. So I need program, and when the program is attached with all those resources, and after attaching the program with all the resources, when your program will provide the output, generate the final output, then we can say that it is a process. Okay. So that's why this definition is very much important, that a process is a program in execution. Okay, so it is not only a program in execution means the program needs to use the set of other resources available to the computer, and with the help of all the resources, the program can complete its execution, and at that time the program will be converted to the process. Clear? Now in the next case, I will discuss the different states of the process. Fine. So as you see, a process goes through different state. That means while you will write the /a dot out, and if you press the enter, your program will be executed by the computer. But how the program will be executed? During this execution phase, during this running phase, the process will go through the several states. What are the states? The states are new state, running state, waiting state, ready state, and terminated state. So this is called the 5 states of the process. Okay. So what is the task of the new state? The task of the new state is to create the process. Okay. So when a process is ready for the execution, so it comes under the new state. Now, from the new state, the process will jump to the running state. So I will discuss what is the flow of the process. Before that, you know the different task of what is the function of the different states. So the next state is the running state. So running state means here the program or process will be executed by the CPU. So running state means the state when the process is executed by the CPU. Waiting state means the process is waiting for some event like the event of IO operation. Suppose you need to take the input from the keyboard, so that is also an operation. You need to take the printout from your printer, that is some IO operation. So the process is, when the process is waiting for some IO operation to be completed, then the process is in waiting state. The next one is a ready state. Ready state means the process is now ready for the execution. When it will get the CPU, it can continue its execution. And the last one is a terminated state. So in this terminated state, the process can finish its execution. So when the process will complete all its operation, then it will go to the terminated state. That means it is the last state which declared that the process has completed its execution successfully or unsuccessfully, whatever the process is terminated. Okay. So in the next slide, I will show you the different state. This is different states of the process and how the states are connected with each other. So here you can see that the new state is connected with the ready state. And one important thing is that with all the states, that mainly with the new state, ready state, and waiting state, some queue is associated. Okay. So with the new state, a queue is associated with the state. This is called the queue. It is queue. With the ready state, another queue is there. So this queue is called the ready queue. This is called the ready queue. And in the waiting state, another queue is associated with the waiting state. So this queue is called the waiting queue. So this is called the waiting queue. Okay. So several queues are associated with different states of the process. Now, when a process is ready for the execution, that means when it can execute, at that time when the program is converted to process, that time all the processes will be stored in a new queue. So suppose there is a program P1 and now this program P1 is converted to process. So the program P1, that means the process P1 will be stored inside the new queue. Now, in this way, several programs like P1, P2, P3, several programs will be stored inside the new queue. Clear? Now, when the process is ready for the execution and it is present in the new queue, so some process will be shifted from the new state to the ready state and it will be stored under the ready queue. So suppose the process P1 wants to change its state and it will change from new state to ready state. So in that case, P1 will be removed from this queue and P1 will be stored over here. Clear? So how the process will be selected from this new queue to the ready queue, that selection operation will be done by the scheduler. So there are a term called the scheduler. So scheduler is the some services of the operating system which perform the scheduling service. So this task of the scheduler is to select a process from the queue associated with the new state and send it to the queue which is called the ready queue associated with the ready state. Now, when a process is present in the ready state, that means in the ready queue, now it has two options. Either it can go to the running, it has only one option, that means it can directly go to the running state. Fine. So, when the process is ready for the execution and the CPU is free, so running state is basically associated with CPU. So when the CPU is free and the process is present in the ready queue, then the scheduler select a process from the ready queue. So in this way, many processes can be stored inside the ready queue. Suppose there is a process P1, P4, P5, P6, so 4 processes are stored inside the ready queue. Fine. So the scheduler select a process from the ready queue as it is queue. So based on the statistics of the queue, that means based on the logic of the queue, that means with the process which will be inserted in the queue first, that process will be taken to the CPU running state first. So depending on the different types of scheduling strategy, the scheduler select a process from the ready queue and assign it to the CPU for the execution. Now, the CPU will execute the process if there is any computation. So, as per you can see the program which I have written just now. So, in that program, there are two instructions. First one is the take the input for A and B, and second one is perform C equals to A plus B operation. So this operation 1 and operation 2, the first operation is the IO operation and the second operation is the computational operation which needs to be performed by the CPU. So when that process with these two instructions jumps to the running state, then CPU examine the first instruction, fetch the first instruction and observe that the process needs to perform some IO operation. So the process will be sent from the running state to the waiting state when a process needs to perform some IO operation. Okay, so in this case, consider this is the two instruction of the process P1, and at the initial state, the scheduler select the process P1 and send it to the CPU running state. Now, when the CPU fetches the first instruction, it found that the first instruction is the IO operation. So the CPU send back the process from the running state to the waiting state. So the process will now come and it will store in the waiting queue. Now if the IO devices, that means IO devices is free, that means the process P1 can get the access of IO devices, then the P1 will take the input with the help of some IO services, and after taking the input, the P1 switch from waiting state to the ready state and it will be stored again over here. Clear? So what happened were, once the P1 will be removed from the first, so consider this is the end from where we can take out the process. So when the P1 will be shifted to the running state, and again from the waiting state, when the P1 will again inserted in the ready queue, it will be inserted at the last, not at the first position. So in this way, the process can change the state from one state to another state depending on its requirement. Now, consider the situation when the CPU examine and check that the P1 needs to perform the IO operation, CPU send the P1 to the waiting state. So at that time, the CPU becomes free. That means the running state is free, no process is associated with the running state. So what happened in this case? In that case, the scheduler will again select a process from the ready queue. Suppose the next process P4 will be selected from the ready queue, and the process P4 will be assigned to the CPU while the P1 is in the waiting state. Clear? So while the P1 is in the P1 is the waiting state, the process P4 is busy with the CPU. Now, when P1 will complete its execution, that means the IO operation, it will go back and it will be inserted again in the ready queue at the end. Now suppose P4, the in syntax of the P4 is nothing but like this one, C equals to A into B. So P4 doesn't need to perform any IO operation. So what happened? P4 has only one instruction which needs the CPU. So P4 will complete its execution, and after completion of the execution, the CPU will send the P4 to the terminate state. That means the process will be terminated. The execution of the process P4 is over now. Now, when the execution of the process P4 is over, then the scheduler now select the next process P5, P6, P1. Among the three processes, it will select anyone depending on the scheduling criteria. And after selection of the process, the scheduler will send it to the CPU for the execution. And then after execution, if all the instruction of that particular process is executed successfully or completed, then in that case, the process will be sent to the terminate state. Otherwise, if the process needs to perform some IO operation, the process will be sent to the waiting state to perform the IO operation. Okay, so in this way, the process can jump from new to ready, ready to running, running to terminate, or running to waiting. Now here you can see there is another arrow from the running state to ready state. Why this arrow is there? This is also a switching. Now let us consider another scenario that there is two processes in the ready queue. One is process P1 and another is process P7. Now P1 is now executed by the CPU. Fine. So I don't have this one. So P1, in my ready queue, I have only two processes. One is P1 and another is P7. So this is my ready queue. Suppose the process P1 is selected by the scheduler. Fine. And this after selection of the process P1, it will be the CPU will execute the process P1. Now, after execution of certain amount of time, so let us say after execution of the T1 amount of time, some event may occur. What are the different types of event? That the time slice can get expired. So consider, as I discussed, that in case of time sharing system, so each process will get the CPU for a fixed amount of time. That is called the time slice. So let us say the time slice is equals to 4 unit. It may be 4 millisecond, nanoseconds, whatever. So it is a 4 unit. Now P1 is now in the running state. So after 4 unit, the time slice will expire. So when the time slice will expire, then the process cannot reside in the running state. It has to go back to the ready queue. Though the process P1 need not perform any IO operation, still the process P1 needs to be sent back. The process P1 needs to be sent back from the running state to the ready state. Okay, so this will happen with the help of the interrupt. Clear? Now, again, when the process P1 will be sent back from the running state to the ready state, so again P1 will be inserted. So P1, suppose the P1 will be inserted in this position. Now the next process P7 will be selected and it will be assigned to the CPU for the execution. And again, when the time slice will expire, again P7 will be sent back to the ready queue and P1 will be selected. So in this way, the process can switch between the running state and ready state depending on the different types of event. So this type of event is called the time slice expire. So in case of time sharing system, time sharing operating system, this time slice, after expiring of the time slice, the process will shift from the running state to the ready state. Again, maybe some situation like that, there is a process P1, P2 and P7. So consider another example where the processes are P2 and P8. Consider two processes, P2 and P8. These two processes are present in the ready queue. So at this, not P2, only P2, no P8 is there. Fine. So consider a process P2 is present in the ready queue. Another scenario of the switching. Now, no other process is present in the ready queue. So scheduler will select the process P2 and it will send it to the running state. So now after sending the process from ready state to the running state, now the queue is empty. No other process is present over there. Now while P2 is in running state, at the same time, at that time instant, another process P8 is inserted in the ready queue. And the P8 is the high priority process. That means the P8 should be executed first, whatever maybe the process is present in the running state. Fine. So like while we are traveling through the road, if there is some VIP person, so all of us, all the cars and all the cars will be kept aside and we will create the passage for the VIP. That means they have the high priority. So like that, if it's considered that P8 is the high priority process. So what happened if P8 is the high priority process, it needs to be executed by the CPU first. So what happened in that case, the operating system forcefully terminate the execution of the process P2. It will send back the process P2 to the ready queue. So P2 will be inserted in the ready queue. And the process P1 will be taken from the ready queue and it will be assigned to the CPU for the execution. So this is another instance, another example of the switching of a process from the running state to ready state. So it is clear that not only to perform the IO operation, the process has to change the state from running state. If the process doesn't need to perform IO operation, then also a process can change from the running state to ready state. So one example is when if the time slice expired, and another example is if some high priority process are there, then the process should be shifted from running state to ready state to give the chance to the high priority process for the execution. Fine. So this is the overall state diagram, overall movement of the process among different states. So the movement in general, the movement is first the process will be inserted in the new state. From the new state, the process will be transferred to the ready state. In the ready state, process is ready, and when it will get the CPU, it will execute it by the CPU. If it has to perform some IO operation, it will go to the waiting state to perform the IO operation. After performing the IO operation, it will go back to the ready state and it will wait to the ready queue to get the another chance for the execution. That is one way, one path. Another part is after when the process is executed by the CPU, at that time the process can be interrupted due to some event, and due to that interrupt, the process has to shift from the running state to the ready state. So that is another way to switch from CPU to the running state to the ready state. And once the process completes its execution, it will go to the terminate state and it will kill itself. So this is the overall description of the process state diagram. Fine. Now the next topic which I will discuss is the process control block. Now what is the process control block? So this is very important data structure of a process. Okay. So while a process is executed by the CPU, at that time, it may happen that process has to change its state. So as you can see previously, the process has to change from, suppose the process has to change from the running state to the ready state. So this is my ready state. So it is my ready state and this is my running state. Okay. So suppose the process P1 is executed by the CPU and it will be transferred from ready to running state, and after completion of and due to some event, due to some occurrence of some high priority process, existence of the high priority process, the process P1 should be shifted from the running state to the ready state. So process P1 will go back to the ready state. So here you can see the execution of the process P1 is not completed totally. So let us say that instructions of for the process P1 are like this one. This is the instruction 1, instruction 2, instruction 3, so, and 10 like that. So each instruction is stored inside the memory. So suppose before, just while the process will be switched from the running state to ready state, at that time process is executing the instruction I2. That means when the process will again go back from the ready to running, that means P1 is now CPU, P1 is executed by the CPU. Now P1 is executing the instruction I2. After execution of the I2, the P1 will be shifted from the running state to ready state. Okay, so that means the P1 is now placed inside the ready queue. Now when again the CPU will be freed, again the P1 will be sent back to the running state. So when the P1 will be sent back to the running state again for the execution, definitely the P1 will not start its execution from the beginning. It will start execution just from that point or a point after that where it left the execution. That means the P1 has successfully completed its execution I2. So again, when the P1 will get the chance for the execution, that means when the P1 is again in the running state, it should execute the instruction I3. Now, how the process P1 can remember that what is the next instruction to be executed? So those remembering things, that means those accounting, those information can be stored in some data structure. And that data structure is called the PCB. Okay, so PCB is the data structure of the process. So what happened over here? When the process will send back from the running state to the ready state, so this program counter store the address. So this program counter will store the address of the instruction to be executed next. Okay, so again, when the process will be reloaded in the running state, from the program counter, the CPU can understand that what is the instruction to be executed. So execution will not start from the beginning. So that is one important requirement of the PCB. So PCB is a data structure which should store the address of the instruction which has to be executed by the CPU. Apart from that, each process has some unique identification number. So that unique identification number, which is called the process ID. So this is called the process ID or identification number. So this process ID or PID is stored inside the process number, that particular field. So in this field, this field identify that this data structure, this information of which is present over here, this information is for which process. There is another important field which is called the process state. So you can see that inside the PCB there are many fields, and all the fields are related with the process which is now in the execution, or which is either in the ready state, running state, waiting state, or in any one of the state. So the process state store the information what is the current state of the process. So when the process is waiting in the ready queue, so the process state is ready. When the process is in the running state, the state is running. When the process is waiting in the waiting state to perform the IO operation, the state is waiting. And when the process will complete its execution, the state is terminated. So the process state store what is the current status of the process, what is the current situation of the process. Now next one is the register. So these registers store all the intermediate operation. So suppose, as I told you, that is here consider the I2 instruction. I2 is nothing but C equals to A plus B, and the instruction I3 is D equals to C into B. Fine. So what you can see that to perform the execution of the instruction I3, I need to remember the result of the I2. So this register stores all the data, that means which we take via input, or all the after in the intermediate execution of the program, the intermediate result which is generated. So that results will also be stored inside the register. So register will store all the temporary data. Fine. There is also another block which is called the memory limits. So this memory limits is also very important. I will just tell you what is the memory limit, but we will discuss it later. In the memory limit, this particular field will store what is the maximum size of the memory where the process will be stored. Because you can remember that if a process needs to be executed by the CPU, the process has to store inside the main memory. So if you store the process, so consider this is our main memory, fine. So this is our main memory. It is our main memory. So this part is used to store the operating system. So if you store the process P1 from here to here, what is the size of this block in the main memory where the process is stored? What is the size of the block? That memory limit is stored over here. The next one is a list of open files. So list of open files is when the process will start its execution and will find out some operation, when it wants to perform some operation. In that case, it needs to take the help of some files, fine. So it needs to take some input from the file. So what are the set of files which are already opened by the process to perform its execution? So all the list of open files are present over here, that file ID. So in this way, you can see the process control block will store the detailed information of the process when the process is when the program in execution. That means during the execution state of a program, the PCB stores all the information about the process so that we can start its execution from any point, and we can also retrieve all the intermediate result. Fine. So this is all about the process control block. Now next, we'll discuss another important part, which is called the CPU switching. Or this switching is also has another important term, so that is called the context switching. Okay. Now what is that? So here you can see here two processes are there. One is the process P0 and another is process P1. Fine. Process P0 and process P1. Now what happened? This executing means the process P0 is in running state. Fine. The execution means the process P0 is in running state. Idle means the process P0 is either in the waiting state or in the ready state. Fine. So you have only one CPU. So when the process P0 is in the CPU, that means the process P1 cannot be executed by the CPU. Now at this point, P0 is in the running state. So at this point, the P0 needs to perform some IO operation or some interrupt occurs, so that we have to send back the process P0 from running to ready state due to the time slice expire or something like that. So whatever, at this point of time, I need to switch the process P0 from the running state either in the waiting state or in the ready state. Fine. Consider we are shifting the process from running to ready state. We consider that. So while you will shift the process from the running to ready state, before shifting, remember, before shifting the process from running to ready state or running to waiting state, all the intermediate data, that means the process P0 maybe perform some computation. So all the intermediate data should be saved inside the PCB, and the address of the last instruction which was executed by the CPU. So the address of the last instruction also needs to be stored inside the program counter. So whatever the status are there in that current point, at that moment, all the current temporary information needs to be stored inside the CPU, inside the PCB. Fine. So before performing the switching, so this all operation will be performed before switching, fine. Before switching from running state to ready state. Before switching from running to ready, the process needs to store all its intermediate data into PCB. Fine. Now, after storing it, the CPU, when it store all its save all the temporary data, now the process P0 will release the CPU. Now, when process P0 will release the CPU is free, no other process is there. So now process P1 can get the CPU. Now, while the process P1 will shift to the running state, before starting its execution, the CPU has to know which instruction has to be executed at this point. So all the data, that means the data which is present, that means the content of the program counter, which is stored inside the PCB. So the content of the program counter which is stored in the PCB, that content should be shifted into the original program counter which is present in the running state. Because this program counter holds the address of the instruction to be executed. Fine. So from the PCB, the content of the program counter should be shifted to the program counter. And all the intermediate data, all the intermediate value should be shifted to the corresponding register. So as you know, there are different registers are there. So all the data should be transferred to the corresponding register for starting its execution. Before starting its execution, all this data which is stored in the PCB, because PCB is nothing but a memory block. So all this data of the stack will be stored into the corresponding stack location. So before starting the execution of the process P1, the content which is present in the PCB, that content should be shifted to the corresponding counter, register, stack. So whatever is present for the execution, what are required, needed for the execution. So all the data will be transferred to the corresponding location before execution. Fine. So after transferring the data from PCB to the corresponding location, the P1 will start its execution. So during this phase, the P1 will complete its execution, start its execution, continue its execution. Now, at this point, again, the P1 needs to switch from running state to the ready state or running to waiting state, whatever. So, if the P1 needs to change its state from the running to waiting or running to ready, again, it needs to reload. That means it needs to save all this data from this program counter. So consider this is our program counter. This is my instruction registers. This is my stack. So all the data again need to be sent back to the PCB before changing the state from running to waiting or running to ready. So all the data which is present in the program counter, instruction register, stack, all the data needs to be sent back to the PCB. So this is called the saved state or into the PCB1. So remember, for each process there is a separate PCB. The process P0 there is one PCB, process P1 there is another PCB. So all the intermediate data should be sent back to the PCB1, and suppose again PCB process P0 will start its execution. So the same operation will need to be performed for the process P0. So data will be taken from the PCB0 and it will be reloaded into the corresponding program counter, instruction register and stack, and the process P0 will start its execution. So this process is going on before leaving the running state. So the main thing is that before leaving the running state, the process has to store its intermediate data to the PCB, and before starting the execution by the CPU, the process has to reload the data from PCB to the corresponding registers, counters and stack. So this changing of the data, that means when it is leaving the CPU, it is to saving the content of all program counter, registers and stack into the PCB, and while it is again resuming its operation, again it is reloading the data from PCB to the corresponding program counter, registers and stack. So this changing is called the context switching. So this is called the context switching. So this is very important topic. Context switching is while the process will change its state, it has to store all its important data to the PCB, or it has to reload. That means when it will switch from ready to running, so it is ready to running state. In that time, we need to store PCB to the corresponding register, counter, stack. We need to store the data from PCB to this one. Okay, but while we will shift from the running state to the ready state. Okay, so if we shift from the running to ready, that means if the change is from running to ready, in that time we need to store all the data which is present in the register, counter, stack, and etc. to the PCB. That means we need to save it. So you can see two situations are there. One situation is running to ready. If I switch on to running to ready, then I have to save the data from here to PCB. And if I want to switch from ready to running, I have to load the data from PCB to the corresponding register, counter, stack. So this phenomenon, this entire situation, entire incident is called the context switching. Okay, so this is all about the today's lecture. So today what we discussed what is process and how the program become process, number one. Number two is what are the different states of the process and how the states are related, how the process will change from one state to another state depending on the situation. And the third one is CPU switching, when the process will change from one state to another state, how it will store it into the data in the corresponding PCB. We also discuss the structure of the PCB. And we discuss what is context switching. So that is all about today's lecture, and thank you for watching my video.